Alright guys, welcome back with this channel again, Artificial and Facts. So now we are going to present about non-parametric method, goodness of fit tests. Let's first, what is goodness of fit test? The understanding of goodness of fit test. In this type of hypothesis test, you determine whether the data fit a particular distribution or not. For example, you may suspect known data fit a binomial distribution. You use a chi-square test, or the distribution for the hypothesis test is chi-square to determine if there is a fit or not. The null and the alternative hypothesis for this test may be written in synthesis or may be stated as equations or inequalities. Now here's the formula for the test statistics for a goodness of fit test, where we can see this O symbol refers to observed values or data. The E symbol refers to expected values from theory, and the K symbol refers to the number of different data cells or categories. Question number 1. What is the chi-square goodness of fit test? Again, what is the chi-square goodness of fit test? 1 minute left. Okay, guys, the time is up. So the answer for the first question is the chi-square goodness of fit test is a statistical hypothesis test used to determine whether a variable is likely to come from a specified distribution or not. It is often used to evaluate whether sample data is representative of the full population. We can use the test when we have counts of values for a categorical variable. The observed values are the data values, and the expected values are the values you would expect to get if the null population hypothesis were true. There are n terms of the form. The number of degrees of freedom is df, or number of categories minus 1. The goodness of fit test is almost always right-tailed. If the observed value and the corresponding expected values are not close to each other, then the test statistic can get very large and will be way out in the right tail of the chi-square curve. Question number 2. What is the chi-square distribution used for? 1 minute left, guys. Okay, the time is up. So the answer for the second question, the chi-square distribution is a theoretical or mathematical distribution which has wide applicability in statistical world. The symbol is used to denote the distribution. The minimum possible value for a variable is 0, but there is no maximum value. The only limitation is that you are restricted to using the significance level and degrees of freedom shown in the table. The question number 3. How can you handle low expected frequencies when performing chi-square? Again, how can you handle low expected frequencies when performing the chi-square? 1 minute left, guys. Okay, the time is up. So the answer for the third question is one solution to this problem is to use Yates correction for continuity, sometimes just known as the continuity correction. To do this, you subtract 0.5 from each observed value that is greater than the expected. Add 0.5 to each observed value that is less than the expected. Then do the chi-square or g-test. The chi-square goodness of fit test example. PPG Industries researched global new car colors in 2012. In this example, we want to determine whether a random sample of local car colors follows the global distribution. To perform this chi-square goodness of fit test, we need to know the global proportions and our regional sample proportions. In this form of the test, the global proportions are the expected values, while the local sample proportions are the observed values. The table below contains the data. The Our State column contains the count of car colors we observe. The global proportions are from PPG Industries. The chi-square goodness of fit test determines whether our local distribution differs from the global distribution. This table displays a frequency distribution and a relative frequency distribution. As you can see, now we are interpreting the test result. The chi-square goodness of fit test for observed counts in variable, or our state, using category names in color. There are many colors: white, silver, black, gray, red, brown, blue, green, and other. From this test result, we get the p-value, which is 0.012. Question number 4. How to distribute discrete probabilities that can model the number of events in a fixed observation space? Again, how to distribute discrete probabilities that can model the number of events in a fixed observation space? You have 5 minutes to answer the question. 1 minute left to answer the question. Okay, the time is up. So the answer for the fourth question, the Poisson distribution is a discrete probability distribution that can model counts of events or attributes in a fixed observation space. Many, but not all, count processes follow this distribution. Consequently, analysts often need to verify whether a set of counts follows the Poisson distribution. The Poisson distribution is discrete because its values must be integers. Because it uses discrete counts, we can use the chi-square goodness of fit test to evaluate whether data follow the Poisson distribution. The chi-square goodness of fit test assesses the differences between the observed and expected proportions. Because the p-value is less than significance level, we reject the null hypothesis and conclude that these differences are statistically significant. We conclude that we didn't draw our local random sample from a population that follows the global proportions. The contribution to chi-square column indicates that the largest differences occur with gray and red cars. By comparing the observed to expected counts, we can see that our sample has a higher proportion of gray cars and a lower proportion of red cars than the global test proportions. Now let us make some example. A safety inspector monitors car accidents at a bustling intersection. The inspector enters the counts of monthly accidents as shown below. There are 5 accidents. Each cell signifies the count of accidents for a month. The full dataset covers 50 months. Now let us perform the test. Interpreting the Poisson test result. Goodness of fit test for Poisson distribution. Data column, which is accidents. Poisson mean for accidents minus 2.24. There are 4 accidents, and by interpreting, we get the Poisson test result, which is p-value is 0.470. Finally, the examples in this post involve comparing the p-value to the significance level. As an alternative to using the p-value, you can compare the chi-square value, which is the test statistic, to the critical value in a chi-square table to determine statistical significance. The two methodologies always agree and allow you to draw the same conclusions.
So question number 5. Testing the hypothesis that a distribution of data, what are the three conditions for a Poisson distribution? An example will show the details of this goodness of fit test. 1 minute left, guys. Okay, for the answer, events are independent of each other. The occurrence of one event does not affect the probability another event will occur. The average rate, or the events per time period, is constant. Two events cannot occur at the same time. Testing the hypothesis that a distribution of data from a normal population. We use the goodness of fit test to compare an observed set of observation to an expected set of observation. In the example regarding bubas, fish, and pasta, the observed frequencies are entries selected by the sample of 1,120 adults. We determine the expected frequencies by assuming there is no preference for any of the four entries. So, one-fourth or 30 adults are expected to select each entry. In this section, we compare one-served frequencies grouped into a frequency distribution with those expect if the sample observation are from a normal population. And for the example, the problems. Using statistical software in section 3.8 on page 69, in chapter 3, we determined that the mean profit on a vehicle for Applewood Auto Group was 1,843.17, and that the standard deviation is it reasonable to conclude that the profit data is a sample obtained from a normal population? To put in another way, does the profit data follow a normal population? We use the 1.05 significance level. And for the solution, to test for a normal distribution, we need to find the expected frequencies for each class in the distribution, assuming that the expected distribution follows a normal probability distribution. We start with the normal distribution by calculating probabilities for each class. Then we use the probabilities to compute the expected frequencies for each class. To begin, we need to find the area or probability for each of the 8 classes. In table 17, 5, assuming a normal population with a mean of 1,843.17 and a standard deviation of 643.63. To find this probability, we use formula. By using this formula, we can convert any formal probability distribution to the standard normal distribution. Formula 7 minus 1 as repeated below. For the solution, as you can see on the table here, z equals x minus in this case, z is the value of standard normal distribution. To illustrate the computation, we select class $200 up to $600 from table 17.5. We want to determine the expected frequencies in the class, assuming the distribution of profits follows a normal distribution. First, we find a z valuable corresponding to $200. This indicates that the lower limit of this class is 2.55 standard deviations below the mean. From Appendix B.1, the probability of finding a z value less than minus 2.55 is 5,000 minus 4,946 equals 0.0054. For the upper limit of the $200 up to $600 class is the formula below. For the solution, finally, to find the area between $200 and $600, the P $200 is smaller than X, bigger than $600, P 2.55 is smaller than Z, then Z bigger than minus 1.93 times 0.268 minus 0.0054 times 0.214. That is about 2.14% of the vehicles sold will result in a profit of between $200 and $600. There is a chance that the profit earned is less than $200. To find this probability, we can use the P x smaller than $200, PZ smaller than minus 2.55 times 5,000 minus 4,946 times 0.0054. For the profits at Applewood Auto Group's and value areas under the normal distribution and expected frequency, we can see on the table 17.6. Logically, if we sold 180 vehicles, we would expect to earn a profit of between $200 and $600 on 3,852 vehicles found by 100214. We would expect to sell 0.972 vehicles with a profit less than $200 found by 180. In general, we use sample statistics to estimate population parameters. We lose a degree of freedom for each parameter we estimate. This is parallel to the situation in section 14.4 of the chapter on multiple regression, where we lost a degree of freedom in denominator of f statistic for each independent variable considered. Graphical and statistical approach to confirm normality. A disadvantage of a goodness of fit test for normality is that the frequency distribution of group data is compared to an expected set of normally distributed frequencies. When we organize data into frequency distribution, we know that we lose information about the data. That is, we do not have the raw data. For that, we can create two cumulative distribution. The first is a cumulative distribution of the raw data. The other is a cumulative normal distribution. 2. We compare the two cumulative distribution by searching for the largest absolute numerical difference between the two distributions. Using a statistical test, if the difference is large, then we reject the null hypothesis that the data are normally distributed. On to the question number 6. What do you want? What do you know about Anderson Darling test? You have 5 minutes to answer the question.
The Anderson-Darling test is a statistical test of whether a given sample of data is drawn from a given probability distribution. In its basic form, the test assumes that there are no parameters to be estimated in the distribution being tested, in which case the test and its set of critical value is distribution free. Question 7. For what do we use Anderson-Darling test? Question 7. For what do we use Anderson-Darling test? 1 minute left. Okay, time's up. The answer is it often used to test if a sample of data came from a population with a specific distribution. It is a modification of the Kolmogorov-Smirnov test and gives more weight to the details than does the KS test. Anderson-Darling test for normality. The dots are close together and appear to form a curved line. The green line, which is mostly covered by the black dots, represents the cumulative normal distribution. The graph shows that the profit data closely follow the green line and that the distribution of profits follow a normal distribution rather closely. Still on. We can use the Anderson-Darling to test to evaluate these differences. For the test, the null and alternate hypotheses are as follows. H0, the population of profits follows the normal distribution. H1, the population of profits does not follow the normal distribution. The computational details of the Anderson-Darling test are beyond the scope of this text. However, using computer software, you can see in the table at the top right of the graph that 5 statistics for the test are summarized. It shows the mean, standard deviation, and sample size. The AD is the Anderson-Darling test statistic used to test the null hypothesis. As presented in chapter 10, every test statistic has a corresponding p-value that is used to make a decision regarding the null hypothesis. Contingency table analysis. Question 8. What is an analysis of the contingency table? Again, question 8. What is an analysis of contingency table? Contingency analysis describes and visualizes the distribution of categorical variables and makes inference about the quality of proportions, independence of the variables, or agreement between variables. Contingency table analysis. Contingency table analysis is a central branch of categorical data analysis and is focused on the analysis of data represented as contingency table. This sort of analysis includes hypothesis testing, as well as estimation of model parameters. Example, applying log linear regression method to fit log linear models to the data. Contingency table analysis is widely used in marketing research, in biomedical research, including drug trials, as well as in the social science. Contingency table. Contingency tables, also called cross-tabs or two-way tables, are used in statistics to summarize the relationship between several categorical variables. The contingency table is a special type of frequency distribution table where two variables are shown simultaneously. Question 9. What is contingency table example? Again, question 9. What is contingency table example? Chi-square test. The chi-square test could then be run on the table to determine if there is a relationship between the two variables. The following contingency table shows exposure to potential source of blood-borne illness in this case, ice cream. From the table, you can see that that 13 people in a case study ate ice cream, 17 people did not. In the above image, there is a knot ratio calculation where the O is the observed value, E is the expected value, and I is the if position in the table. The sigma is the summation symbol. The following picture shows that what your contingency table might look like with your data, plus the result from running a t-test on the data. A small t value means that there is real relationship between the categorical variables. Large G means value means that there is a definite correlation between the two variables. For example, a researcher might be investigating the relationship between AIDS and sexual preference. The two variables would be AIDS and sexual preference. The question is there a significant relationship between AIDS and sexual preference? As there is some pretty strong evidence that sexual orientation is linked to a higher risk of contracting AIDS. It's not surprised that the G value is rather high. However, the note under the result states that for cells for 66.7% have expected count less than 5. Generally, if this over 25%, the result could be due to chance alone. Therefore, the results from this particular test are not statistically significant. Question 10. What is contingency table in a chi-square test? One minute left. Marginal and conditional distribution in contingency tables. Contingency tables are a fantastic way of finding marginal and conditional distributions. These two distributions are a type of frequency distribution. Marginal distribution. These distributions represent the frequency distribution of one categorical variable without regard for other variables. Conditional distribution. For these distributions, you specify the value for one of the variables in the contingency table and then assess the distribution of frequencies for the other variable. In other words, you condition the frequency distribution for one variable by setting a value of the other variable. Number of categorical variables. It must have at least two categorical variables to create a contingency table. When you have two variables, it's a two-way table. If you have three, it's a three-way table, and so on. For example, suppose we run a computer store and record the sales using the two categorical variables of gender and computer type. Those variables create a two-way contingency table. If we add third categorical variables for store location, it becomes a three-way table. How do you present a three-way table? Because contingency tables display in two dimensions, you need multiple tables to represent anything more than a two-way table. If there are four store locations in this three-way example, we'll need to use four two-way tables. Each table displays gender and computer type for one location. Numbers of rows and columns. The rows represent values of one categorical variable, while the columns denote the values of another. Analysts indicate the number of values for each variable by describing this table as an AXB contingency table, where A represents the number of rows and B signifies the number of columns. For example, at our computer store, gender has two possible values and computer type. Computer type has two values, PC and Mac. Hence, we have a 2 times 2 contingency table. If we add third type of computer as new column, it becomes a 2 times 3 table. That's all for today. See you in the next topic. Thank you.